Hey, the final section in this chapter is going to show us some ways that exponential and logarithmic functions are used in real life. Whenever you teach logarithms, somebody always asks that question, when would I ever use this in real life? Well, the answer is in math and science, they show up all over the place when you want to start modeling functions. Exponential functions in particular model lots of phenomenon, and then if you want to solve those, you have to use logarithms. But logarithms themselves model some things like the Richter scale and decibel level, as we'll see. We're going to start with exponential. So any quantity that grows exponentially, we could write an exponential growth function. And it turns out there's some advantages to using e. You could always write an exponential function as a times b to the t. We've looked at that format before. But you can replace b with e to the r, or any letter you want here, but we have our initial value. If you plug in 0, e to the 0 would be 1, and you would just get this n sub 0. So this is the notation for the initial at time 0, the initial population, if we think of this as being a population that's growing. And r would be the growth rate, and of course t is time, and this would give you the population after that time. So if you think about the a, b to the t model, you just replace b with e to the r, and you could figure out the appropriate r. Again, some advantages to that. You know, when you're looking at a, b to the t, if b is bigger than 1, it grows. If b is between 0 and 1, it decays, which is not too bad, but you have to think a little bit about that. In this format, if this coefficient, if the r here, if the power is positive, it grows, and if it's negative, it decays, because that's when e to the r is bigger than 1 or between 0 and 1. Also, we have natural log on our calculators, and it allows us to solve equations more easily if we use e. So here's a problem. We have some bacteria. The initial count in a culture is 625 bacteria. A biologist later makes a sample count of the bacteria in the culture and finds that the relative growth rate, the little r that we need, is 35% per hour. So part A, find the function. Find a function that models the number of bacteria after t hours. Then part B, use that function to estimate the count of bacteria after 10 hours, and then sketch a graph of the function. Okay. So what do we know? We know the initial value is 625, so that's going to be the n sub 0, and then we have e to the rt. R was actually given to us. It's the relative growth rate. You have to always convert to a decimal. 35% if you divide by 100 is 0.35. So this problem, they basically gave us the numbers we needed, and we just feed them into the formula. So our population of the bacteria, n of t, is 625 e to the 0.35 t. And then for part B, you would just plug 10 into that for t and evaluate. And you wind up, once exponential functions start growing, they grow fast. You've got almost 21,000 bacteria, and you plug 10 in. And then the graph, well, you could just plug it into your calculator, but you're going to have to figure out a good window. You can read my note there, but I'll show you some screenshots of what I did. So I plotted 625 e to the 0.35x. You have to use x on the calculator instead of t. And so for my window, you can pick whatever you want for the x-axis. We're talking about hours, so I decided to go, I always want to go a little negative to see the axis. I went -2 out to 20, which would cover 20 hours. And I did a scale of 2 since I was going out to 20. And then in the y direction, just by looking at some of the values, I saw it had to be really, really large. Like we already know at 10 hours it's 20,000. So I picked a scale of 10,000 and went to 50,000. And if it doesn't look good, I could change the window, but you get a pretty good graph there, exponential growth. Okay, another exponential growth problem. Population of the world is perhaps growing exponentially, or we can at least model it that way. In 2000, the population of the world was 6.1 billion people, and the relative growth rate was 1.4% per year. That's very fast and a little alarming to people, so it's claimed that a rate of 1% per year would make a significant difference in the population in just a few decades. Test this claim by estimating the population of the world in the year 2050 using the relative growth rates of 1.4%, what it actually was in the year 2000, and then 1%. Of course, a lot of time has already passed since the year 2000 when I first got this problem from one of the textbooks, but anyway, we're going to solve it with these numbers. And then part C, draw a graph again. So the idea is we're going to look at it with these two different growth rates and kind of look at the difference. So you have to find the functions first. In both cases, we're going to use 6.1 as the initial value. You could convert that and put all the zeros if you wanted, but we're just going to understand that we're measuring in billions. So our initial value is 6.1 billion people. And we have e to the, if you convert 1.4% to a decimal, you get 0.014. Be careful with the decimal place. And you can plug 50 into that and just, crank out that number with your calculator. You get 12.28 billion people. And then for part B, to compare there, we do the same thing with the 1%. So instead of 0.014, we use 1% for the R value. And you plug 50 into that and evaluate, and you get 10.06 billion. So both those numbers are large, but they actually differ by 2 billion people, which is a pretty large amount. And then for the graph, again, you could play around with the window a little bit, but we're going to graph on both. You can see the window that I wound up deciding to use by really experimenting a little bit and looking at the numbers. But there's the graphs, and the point is, over time, they separate by more and more. The 1.4% just grows so much faster than the 1% that over time it does make a really big difference. Okay, let's do a related problem. The population of the world was 6.1 billion in 2000. The estimated relative growth rate was 1.4% per year, like the previous problem told us. If the population continues to grow at this rate, when will it reach 150 billion people? Well, we plug in everything we know. We plug in the 150 for the output, and we can solve with logarithms for the time. So we have 6.1 e to the 0.014t, the same model as the previous problem. But now we want to figure out what t would make that equal to 150. So this is similar to our continuous compound interest problems. We solve a lot of problems that look like this with exponential growth. You divide both sides by that initial value. You get 150 divided by 6.1. I always like to wait and punch everything in the calculator at the end so I don't have to round off, get any round off error. But you take a natural log of both sides, and again, that's one reason we use e. Natural log and e just wipe each other out, and you just get 0.014t on the left-hand side. And then we have natural log of whatever 150 divided by 6.1 is, and you divide by the coefficient 0.014, and you'll wind up with your answer, which I did there on the calculator screen. You get 228, so you add that to 2000. This is the number of years since 2000, so sometime during the year 2228, if the growth rate was exponential at 1.4% per year from 2000 on, that's what would happen.